In this lecture, we are going to discuss the probability of default model in more detail. Let's get started. In the PD model, we are interested in assessing the probability that a borrower defaults. To do that, we can use the observed borrower defaults. As you can remember, we created a default definition that assigned all borrowers to one of two possible outcomes: default or bad, and non-default or good. More precisely, we set all loans with statuses charged off default, does not meet the credit policy status charged off, and late 31 to 120 days to default or bad, and all other loans to non-default or good. In data science, there are many models that can predict a binary outcome. But as we've already mentioned, the model must be easy to understand and interpret. In other words, even people who don't know much about data science should be able to figure out how it works. This is one of the main reasons why probability of default is typically modeled in the easiest way to interpret, through logistic regression. Let's see how it works. In terms of probabilities, the logistic regression model predicts the probability of an event occurring. So we are basically asking the question, given input data, what is the probability that a borrower defaults? We call the regression logistic, as the curve that predicts the outcomes is defined by a logistic function. Let's look at an example with a single independent variable, say annual income. As our initial data exploration showed, the proportion of borrowers who have defaulted is greater among borrowers with lower annual income and rather low among borrowers with higher annual income. Hence, the greater the annual income, the lower the probability of default. We mentioned that when we estimate the model, we are going to focus on the positive outcome, or non-default. This is also the reason why in our datasets we assigned a value of 1 to good, or non-defaulted borrowers, and a value of 0 to bad, or defaulted borrowers. If we plot a logistic curve between the good, bad dependent variable and the annual income independent variable, it will have an S shape and will be bounded by 0 and 1, like this. These two properties are one of the biggest advantages of this type of regression. Okay, you may have noticed that a logistic regression is similar to linear regression. Speaking in algebraic terms, the linear regression equation looks like this. The dependent variable equals a linear combination of the independent variables plus an error term. Under the logistic regression model, the probability of an event can be represented as the exponential of a linear combination of independent variables and coefficients, divided by 1 plus the same exponential. If we transform this expression in a certain way, we will get the probability of the event occurring divided by the probability of the event not occurring equals the exponential from above. That's a very nice form, as the left-hand side has a very intuitive interpretation. It's called odds. For instance, if you throw a fair coin, there are two possibilities, heads or tails. I prefer heads, so what's the probability of getting heads? 50%, right? But what are the odds of getting heads? Well, they are equal to the probability of getting heads to the probability of getting tails. That's 50% to 50%, or better, 1 to 1. What about a fair die? Obviously, I want to find the odds of getting a 6, so the odds are the probability of getting a 6 to the probability of not getting a 6. 1/6 divided by 5/6 equals 1/5. So the odds are 1 to 5, much like the odds bookies give. Okay, we're ready to go back to the logistics model. So the odds are equal to this exponential expression. We know that the log is kind of the opposite of exponential, so I'll take the log of both sides. What we get is a very elegant model. The log of the odds is equal to a linear model. Not any linear model, but precisely the same as the one we had in the linear regression, with no explicit error term though. Another assumption of the linear model was that the expected value of the error term is 0, thus for all practical purposes, the two models are equivalent. Cool! So the basis of logistic regression is linear regression. Given that the model is not very different, our main concern from now on will be how to interpret the coefficients of a logistic regression. What is specific for the probability of default model is that all of the independent variables are dummy variables. In other words, they are indicator variables with a value of either 0 or 1. This means the coefficient for such a variable shows the exact difference in logarithm of odds units between an observation for which the dummy variable equals 1 and an observation for which the dummy variable equals 0. Let beta be one of the coefficient for the independent dummy variable x. Imagine we have two observations, one with the dummy variable having the value of 1 and the other the dummy variable having the value of 0. Then, if we subtract the equation for the first observation from the equation for the second one, we get the difference of logarithms for odds equals beta 1 times the difference for the values of the dummy variable. This last difference is always 1, because it is the result of 1 minus 0. So the difference of logarithms of odds equals beta 1 times 1, or simply beta 1. You probably remember that the difference of two logarithms of two numbers equals the logarithm of the ratio of these two numbers. So the logarithm of the ratio of odds of the two observations equals beta 1. Okay, now let's take the exponential of both sides. On the left-hand side, an exponent raised on a power logarithm with a base of an exponent equals the argument of the logarithm. So, what's left is just the ratio of odds. Thus, the ratio of odds of an event occurring for an observation with the dummy variable having a value of 1 to the observation with the dummy variable having a value of 0 equals an exponent to the power of the regression coefficient of the dummy variable. Let's see a quick example with numbers. Say we estimate a logistic regression model and we get that the log of odds of non-default to default equals minus 3.91 plus 0.24 times a dummy variable that indicates if the borrower has higher education or not. To be more precise, the dummy variable has a value of 1 when the borrower has higher education and a value of 0 when the borrower does not. So the ratio of the odds of a borrower being good when they have higher education to the odds of the borrower being good when they don't have higher education equals an exponent raised to the coefficient of the higher education dummy variable, which is 0.24. This equals 1.27. Therefore, the odds of being good when the borrower has higher education are 1.27 times higher than when they don't have higher education. So if the borrower has higher education, the odds of them being good are 27% higher. So that's how we interpret the coefficient of a dummy variable in a logistic regression model. After this short theory lesson, we can proceed with the PD model. Thanks for watching.